Okay, so last time we were into chapter 2, we got a little bit more to go. Amanda, what we talked about last time is a very important calculation or ways that you need to kind of show your work, show your calculations. As we talked about, they want you to basically show all your work as you go through 1A, 1B, and all the chemistry series through dimensional analysis. And dimensional analysis, again, is really the way where we use conversion factors and we use units to basically cancel out the units. So if we have several units along the way, we want to set it up like this where we can see the different units. We can see them canceling out. We can see sort of what is left along the way. So again, we're multiplying everything across the top. And we're dividing by everything that's basically on the bottom. But this is the way they do want you to sort of show all your work, even things that maybe are kind of like a plug and chug that you can still sort of show through dimensional analysis. They definitely want you to kind of do that approach. So since we're really multiplying and dividing, opposites cancel. So we want to get rid of a unit. It needs to go in opposite locations and they will cancel each other out. Again, it's essentially like we talked about, dividing the same number by the same number gets you 1. If you divide the same unit on top by the same unit on the bottom, basically equals 1, and they cancel each other out. So it's really important to show your work in the dimensional analysis. We also talked about calculations and significant figures. Remember that when we multiply or divide, it is the sig figs we're looking at, and it is the least number of sig figs. So whatever number in your calculation, if you're multiplying or dividing, has the smallest number of significant figures, that's how many significant figures your answer should have. When we add and subtract, it's a little bit different. When we add and subtract, we are looking at decimal places. So we're looking at decimal places. And it's also the least. So if you have a set of numbers that you're either adding or subtracting, the number with the least number of decimal places is how many decimal places you should take your answer to. As we talked about, though, you should keep in mind that obviously will give you a certain number of significant figures, which might be important if you take that number and continue on with the calculation. You want to make sure you keep those things straight. Also, if you do some type of combination of all those things together, you've got to really kind of follow and keep track of all the parts of the calculation. And as we talked about, you really don't want to round to the very end. So you want to keep track of where everything probably should end up. And at the very end, you should sort of round it up, or round it, not necessarily up, but round it off to the proper number of digits. You shouldn't do a lot of rounding in the intermediate steps if it's a multiple sort of calculation where you're getting numbers and you'll find yourself kind of far away from the right answer if you kind of keep rounding at every step along the way. Also, it's important when we do something in dimensional analysis that we talked about, there's 2 types of units, right? There's sort of the English units, there's the metric units. And for sure, if you're using any type of English to English conversion or metric to metric conversion, those guys are considered exact numbers. If you have something like 1 inch is 2.54 centimeters, or maybe 1 pound is 453.6 grams. These also are considered exact conversions, and they are basically exact numbers, which basically means, as we talked about, they can have as many significant figures as you want. So what we typically do with those type of numbers is we ignore them in calculations in terms of trying to figure out how many significant figures our answer should end up with. The one place where you really should look is if you do kind of cross over English to metric, and it's obviously not one of those couple we just talked about a second ago. You should look at the number in that conversion factor, not the one that's a 1, but the other number that's there, and take those significant figures into account. I would say a lot of times you'll be in a pretty safe place, probably correct or pretty close to where you should be. If you kind of look at that original number, if it's just doing a conversion, a lot of times it does end up being kind of that original number that you look at as everything in the middle of the calculation. Again, not 100% of the time, but a lot of times will be sort of an exact number. Any questions on any of that stuff we talked about last time? Okay, so what we got left here is to talk about density officially. We did the density lab the other day, but density is defined really as the amount of matter an object possesses per volume. And obviously it is really the mass divided by the volume. The differences in density really determine whether or not a object will sink or float. So for example, if we have water, which for the most part, if you ever sort of need the density of liquid water, it usually is 1 gram per milliliter or 1 gram per cubic centimeter. A reminder that a milliliter and a cubic centimeter are basically the same deal. So they're like the exact same sort of unit. So that's the common value. If you ever find yourself like, I need to use sort of the density of water, that's typically what people use. It should be noted that density actually does change with temperature. So as the temperature changes, so does the density of a substance. But that is a pretty universal one for liquid water to use. So if you ever need it and it's not given to you, you can probably, again, safely kind of use that value. But if we do have something that's more dense than water, it will sink. And if something is less dense than water, it will kind of float. You know, for example, if you took 2 cans of soda, one is regular soda, one is diet soda. If I put them both into like a bucket of water, will they both sink? Will they both float? What will happen? Actually, one will sink and one will float. The one that will float would be, which one do you think? The Diet Coke actually will float, because if it's a diet beverage, it usually has like artificial sweetener, right? Regular full strength beverage actually has a lot of sugar. So the real stuff will sink to the bottom. The Diet Coke sort of will float around. It's a nice party trick. You should try it. Holiday weekend coming up and all that good stuff. But obviously, if we have something that is less dense than water, it will obviously sink in it. Same thing with sort of liquids as well. You know, if we have some liquids with some different densities and you put them together, maybe in the same graduated cylinder, we will get some separation that will occur. You know, so you'll have these different sort of layers where the more dense should be towards the bottom layer. The less dense would be towards the top layer here. If you know you threw something solid in there, maybe it just kind of hung right about there. Obviously that, whatever I just drew there, that dot would be obviously more dense than anything above it, right? In terms of the liquids, it'd be less dense than, you know, what is below it. So we saw the equation, which is the density is equal to mass over volume. And once again, this is a cubic centimeter. But we also talked about the importance of being able to rearrange this. So if we are solving for volume, we would multiply it to the other side and divide the density back. And the volume would be our mass divided by density. And if we want the mass, we would just multiply the volume to the other side, and that would give us our mass is equal to volume times the density. I think I put up in lab that's kind of DMV triangle, right? So sometimes people remember it sort of this way. And whoops, you can do that as well. Important to obviously know that formula, right? It will not be provided for you, and to be able to properly rearrange it as well. In terms of units, as we have on the bottom there, grams per milliliter and grams per cubic centimeters, typically the units that you see for density for solids and liquids. We really don't get too much into this, but when you take 1A and you talk about gases, you'll probably learn how to calculate the density of a gas using the gas law. But typically gases densities are given in grams per liter. But for the most part, for this class, grams per milliliter, grams per cubic centimeter, the common units that we see for density. Questions on that there? All right, so why don't we try one here? A block has a volume of 25.3 cubic centimeters. Its mass is 21.7 grams. Calculate the density. here. So obviously we're looking for the density. So we want to look at our density equation, which would be our mass divided by volume. We obviously have the mass given to us, and we also have the volume given to us. So really in this one, we're just going to plug it in there. That would give us 21.7 grams divided by 25.3 cubic centimeters. And if we do that there, looks like we end up with 0.858. That looks like 0.858. Now, in terms of the units, clearly the units do not cancel. So with density, the number always stays with the grams and is per basically 1 milliliter. I guess cubic centimeter would be the right unit there. So, right, cubic centimeter. Any questions on that calculation? Now, in terms of significant figures, we're really dividing here, right? So we're going to look at sig figs of each of the numbers. They both are 3. So that is why we rounded it there to 3 significant figures when it's all said and done. Any questions on that one? So we talked about sort of getting volumes, and there's really kind of 3 ways that we do get volumes with density a lot of times, and we did it in the experiment the other day. One way, obviously, to get a volume is to just simply read the meniscus, right, and take a volume reading properly. Another way, if we had some type of solid like we did in lab, you can measure the length times the width times the height. Again, all in sort of length measurements. When you multiply them together, that then gives you a volume like cubic centimeters. The last and very common way with density, as we did in the experiment, is to get the volume by displacement. So once again, volume by displacement basically means is we start with a container that has a certain amount of volume in it, and you take any type of solid object and basically drop it in there. What's going to happen to the level there of the liquid is it should rise because it's basically being displaced by the solid that's going in there. You would take a final reading here, and really the volume of the object that went for a swim would be the difference in those 2 volumes. If I could draw a straight line difference between those 2 volumes. And we can find that by, once again, taking the volume of the object, volume final minus the initial volume. So that is a really, really common way and sort of a pretty simple way to find the volume of something that is a solid. So a picture here to sort of demonstrate that. Here, obviously, before she takes a dive into the pool, the initial volume is right there. Obviously, when she goes in, she's going to displace that liquid, and her final volume comes up here. So once again, if we take that difference in volume, or the change in volume, will give us the volume of her. Hopefully this is not just decoration, but a staircase so she can get out of the tank and not has to hold her breath all day. We'll hope she'll be okay. I think she's made it to every edition of the book, so I think she's okay along the way. So let's take a look at one of these things. A student fills a graduated cylinder to 25 milliliters of liquid. She then puts a solid in it. The volume goes to 33.9. The mass of the solid is 63.5. Calculate the density there. So take a moment or two to see what you come up with. Okay, let's take a look. So this is obviously the exact situation we were just talking about. We basically got 25 milliliters there of our liquid. We're going to throw a solid in there, and our volume then rises to 33.9 milliliters with our solid in there. We obviously want to calculate the density, which is mass divided by volume. So we do have the mass given to us, but we do have to find the volume by displacement here. So we're going to take our final minus our initial here. So the volume of the object would be our final volume, which was 33.9 milliliters, minus our initial, which was 25 milliliters. That's going to give us 8.9 milliliters. So now we do have the volume. So we can put it in here. Our density will equal 63.5 grams divided by 8.9 milliliters. And that will give us a density of 7.1 grams per milliliter in this particular case. First off, any questions on that calculation? Now, sig fig wise for our answer is really based off of what here? Is really based off of the volume calculation we did. So we were subtracting, so we should go to decimal places. They both have one decimal place. That should give us an answer with one decimal place. But now this does have two significant figures. So when I do my very final step, which is dividing three significant figures by two significant figures, that is why my answer should end up at two significant figures. Any questions on that? So once again, it's really important to sort of keep track of everything that you're doing. As if you just sort of blanket look at the problem and you go, everybody's got 3 sig figs, so I should probably leave it at 3 sig figs. But again, because of that sort of subtraction that we did, you got to take that into account. Any questions on that one? So here's some density of some common substances. So as I mentioned before, that is pretty much the value that we use for water if you ever need it, and that's would be liquid water. By the way, water is an unusual substance that we'll talk about in a later chapter as well, but water is one of the few substances wherein there's liquid state. That's why when we put ice cubes in our drinks, right, they end up floating to the top, right? They don't sink and stuff like that. And that's because when water comes together in the solid version, because of the way they hydrogen bond together, it creates a lot of really open spaces between the different water molecules, which obviously bloats it, if you will, right? Increases its volume. And if we think about, which is mass divided by volume, gives ice a greater volume on the bottom, right? So mathematically, we end up with actually a smaller density than in the liquid phase. And that's an unusual sort of process there, or characteristic substance. Everybody above there on that list should float in water, right? Everybody below water there on that list there should really sink. As we talked about, if you have some liquid with different densities, we will get the layering that basically will occur. So you definitely should know the density of water is 1 gram per milliliter, because you sometimes need to use that a lot and it's not really provided for you. And it's just a common number. All right, let's try one last one here. How many? A student needs 150 cubic centimeters of salt for an experiment. The density of the salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt would they need? A reminder of a conversion we talked about that you should know, 1 pound is 453.6 grams. All right, take a moment or two, see how many 1 pound boxes we're looking for. Okay, let's take a look. So obviously we're dealing with density. So if you're not sure, that's a good place to start, which is the mass divided by volume. In this case, we have 150 cubic centimeters. That is a volume. We also have the density given to us, which is 2.16 grams per cubic centimeters. Now, you frankly can use density like a conversion factor. Again, the number always stays with the grams. It's always 1 milliliter or 1 cubic centimeter. So you can sort of think of this as well as like a conversion factor where you could flip it around and kind of put the grams on the bottom. So here, if we took more of a dimensional analysis approach to solve this problem, we could take 150 cubic centimeters. Once again, we want to go opposite in terms of our units to cancel them. So we would use this just like that as a conversion factor. That would give us 2.16 grams per cubic centimeter. Once again, the cubic centimeters there would cancel, and that would basically give us our mass, right? Which is the one thing we're really looking for. And again, mass would be volume times density. That would give us 324 grams of salt in this case. At this point, we would look probably at some significant figures, right? First number's got 2 significant figures, right? Our density value there has 3 significant figures. So really my answer should end up with 2 significant figures in this case. So you should end up with about 320 grams of salt. Should I put a decimal point at the end of the 0? I shouldn't, again, because then that would give you 3 significant figures. We also want to make sure that we actually answer the question. The question really was asking how many boxes of salt would we need? We really just need one box, right? As one box has 453.6 grams, so we'll have a little left over to share. So I didn't really round here anywhere until the very end, right? Well, in this case, this would be kind of like the end of my calculation at this point. So that's why I rounded it. If your question was if we took like the 324 grams and continued on with that number, I again probably wouldn't round at that point. I would probably go with this 324s in my calculator and continue on to the next step. Say maybe we did one more calculation, and then at that point I would round and stuff. But technically speaking, this is sort of the end of this calculation. So that's why I would have rounded to 320. Which in reality is not even really what the question is asking. It's just actually asking this, right? How many boxes would you need? Is that, so, but that is sort of the answer, would be the final answer in this case. But you definitely shouldn't round until you're sort of all done with all the parts of it, but you should keep track of it. Other questions? Yeah. Yeah, so I in this type of question, one box would have been sufficient. Unless I specifically asked, like, how much of that one box or how much of a box would you need, something like that. Then you would obviously use like, one box, 1 pound would be 453 grams, and you could maybe figure out how many pounds of salt you would need and stuff like that. Yeah. So if that was sort of the question, like how many pounds of salt you need, you would do one more conversion. And to answer the question was asked with earlier, you would keep the 324 at that case and do that conversion part of it. Other questions? Okay. All right, questions on density. Obviously, you need to be able to calculate the density, the volume, the mass. You need to be able to figure out volumes, either length times width times height, taking a volume reading, or obviously volume by displacement. Any questions on any of that? We're not going to do specific gravity, so that is it for chapter 2. Any questions? All right, we're going to roll to chapter 3. Just give me a second to kind of get it up here. So this is chapter 3. We're going to talk about matter. We're going to talk about the different states of matter a little bit more, and we'll also talk about mixtures and all those type of things. So obviously, I think we might have talked about the first lecture or so, but just in case not, obviously there are 3 states of matter. There is, I guess, the solid state, where things once again are packed in there pretty tight to one another. They can't have enough energy to kind of move around each other, which is why they're pretty much rigid and stuff like that. We also have the liquid state, where things are still relatively sort of tight to one another. Again, there's a little bit more room for movement, a little bit more energy, so they can pass each other. Why liquids are fluid, right? And obviously when we get to sort of the gas phase there, pretty much everybody has broken apart. And as we'll talk about when we get to the gas chapter, obviously they're flying around making collisions. I'm sure the person next door enjoys me knocking on that door. Is causing pressure that we associate with gases. There's also some transitions which are important as we go from one to the next, and a reminder that if we have solid going to liquid, that is the process of melting. Liquid going back to solid is the process of freezing. Liquid going to gas is evaporation or vaporization, sometimes called. Condensation is when we go from gas back to liquid. When we go from solid, skipping the liquid phase and go directly into the gas phase, that is sublimation. And going from gas back to solid, also skipping the liquid phase, that is what is known as deposition. Once again, as we'll talk about in a later chapter as well, might have touched upon it early on as well. This process here, both of those processes occur at the same temperature. That is usually the normal melting point or melting point or freezing point of a substance. right exactly at that melting point or freezing point, you really have both phases in equilibrium with each other. So for example, water is 0 degrees Celsius where that occurs. And we have some ice and liquid water really happening at the same point, exactly at 0 degrees Celsius. Not to get a little bit above, you get liquid water, a little below, really ice. Same thing here, evaporation and condensation also occurs at the same temperature. That is the normal boiling point of a substance. And exactly at that boiling point, which again for water would be 100 degrees Celsius, you got both phases happening. You got some liquid there, you got some gas. It is at the surface of the water, you always have that exchange sort of happening. The surface of a liquid, guys jumping out into the gas phase, guys dropping back into the liquid phase. In terms of energy, also important, we'll talk about in the next chapter that we talk about in terms of energy, but obviously as we go from solid to liquid to gas, those are all what are referred to as endothermic processes, which means energy is absorbed. You got to put energy in, say to your ice cube, it starts to melt. You put more energy into liquid water like we did before, we'll do today, it will start to boil, right? Going the opposite way there from gas to liquid to solid, those are all what are referred to as exothermic in terms of energy, which means energy is released in that case. So energy is released in that case as those processes go. So again, a lot of things involving matter really deals with like phases changing and how substances do change. Any questions on that there? So matter, as I mentioned, is really the stuff the universe is made out of. It's really anything that has mass and occupies space, which is pretty much everything. As we just saw there, my award-winning diagrams. Solid, again, has a definite shape and very difficult to change the shape of it. They're said to sometimes be rigid. Clearly, like this board here, I can't just take it off the wall and like fold it up like a piece of paper or anything like that, right? It's very hard to change the shape of it. Liquid, on the other hand, things like water, gasoline, they do not have a definite shape, but they do have a definite volume. So what that means is if you have, say, 5 milliliters of water, and you take that 5 milliliters of water and you put it in the trash can, it obviously will take the shape of the trash can. You take the same 5 milliliters of water and put it in a water bottle, it'll take the shape of the water bottle. Put in one of those silly straws that go around and around, right? It'll take the shape of the silly straw. But if you started with 5 milliliters of water and all you did is transfer it from one container to the next and you weren't a klutz and spilled it all over the place, you should still have 5 milliliters of water all the way through that transfer. Again, provided you don't spill it. Gas, on the other hand, again, it's that state of matter where everybody is really flying around. Because they're flying around, we think of gas, an ideal situation that basically will fly uniformly. They're flying around. And part of gas laws that we'll talk a little bit about in this class, and you'll talk more about in 1A, is the idea of like an ideal gas. And in an ideal gas, we actually think of the volume of the gas itself as actually the volume of the container it's in, because it flies around and fills it uniformly. And under ideal conditions, that's what we look at. We actually don't think about the actual volume of the gas molecules itself, but because they're uniformly flying around in that container, we sort of focus on the container and its volume as being really the volume of the gas that we may be dealing with. So obviously here's some pictures of our liquids taking the shape of all those silly shapes, I suppose. Here's our water. And as I mentioned before, water is an unusual substance. And as you can see here, water is held together by what is referred to as hydrogen bonding, which we'll talk about in a later chapter. But as it hydrogen bonds with itself, as it moves from liquid to solid, as you can see, as our conversation earlier with density, we get all this kind of empty space that's occurring there between the different water molecules that again sort of bloats this volume. And just simply mathematical looking at it, as we talked about, that means that number is going to be larger, and that does give actually our solid water, a less dense version there than our liquid water. By the way, as we go from ice to water to steam, that is all water, right? So that's all same thing, it's all H2O along the way. There's no real change in what that substance is. Now, the state of a given matter depends really on the forces that hold them together. The forces they're talking about are what are referred to as intermolecular forces, and we'll talk about it in a later chapter. But intermolecular forces are really the forces that hold one molecule together with another. So intermolecular forces is what they're really talking about here. And basically holds one molecule together with another. So the idea here is, and we'll talk about these things in a later chapter, but the stronger that intermolecular force, the less likely that thing will sort of exist in the gas phase, because they're basically held together, the molecules. In order for it to get to gas phase, it got to break apart. So strong holding together of each of those molecules is going to allow them to stay together and really not go into the gas phase. Now, on the other hand, if you have something that is held together by really weak forces, they will no problem go into the gas phase, because you don't need a lot of energy to get them apart, so they'll be able to fly around. Like when you light a Bunsen burner and the methane comes out, right? That methane is held together by super weak intermolecular forces, which means you don't have to convince it a lot to kind of go into the gas phase. So that's what we'll talk about later in relationship to that is sometimes you hear the word volatile, right? Something's volatile. And that basically means it's not held together by very strong forces. So pretty much as soon as it gets the opportunity, it's going to want to break apart and go into the gas phase. So that's basically what that means, and is able to do so. So here's a table that you have in your book of some of the states, solid, liquid, and gas. And obviously you do need to know sort of the differences between them and some examples of each of those. So let's talk a little bit about physical and chemical properties. A physical property is basically one that can be observed without changing the identity of a substance. Typical physical properties are things like odor, color, volume. The state is a very common physical property. Is it a solid, a liquid, a gas? Density, melting points, and boiling points. So physical properties are properties where, it has really nothing to do with any type of changing that's going to occur, but just these sort of properties that we can sort of visually observe in a lot of cases are not really depending on some type of reaction to occur. We can measure the melting point, for example, of ice by heating it. But as that ice is converted to water, it is still, again, H2O. So ice and water is both H2O. It has not fundamentally changed. So a lot of times physical properties are related to physical changes. And physical changes are ones where what you start with and what you end up with is fundamentally still the same thing. It may just look different, may have a different appearance, but the core of a physical change is that what you start and what you end are basically exactly the same thing. So a physical change. So what you start with and what you end up with are fundamentally the same in a physical change. And the example of that is what we were just talking about a second ago, which is our ice. Obviously, if we melt our ice, we get liquid water. If we continue to heat our ice, we get steam, right? That basically forms. All three of those things, ice, liquid water, and steam, they're all fundamentally the exact same substance. They're all basically water, H2O. It's just they're in different phases, which are different physical sort of properties for these things. So there is no sort of chemical change happening in each of these cases. They're just physical changes. If I took a piece of paper and I ripped it up into a whole bunch of small pieces, that is still a physical change because each of those small pieces are still fundamentally paper, right? I didn't change it into anything. It just looks different. If you got a wrinkled shirt and you iron it, still a shirt, right? Just less wrinkles in it. So anything where you start with and when do you end up with is fundamentally the same substance. Those are definitely physical changes. Any questions on that there? There's our example of heating that up there. And that is different than a sort of chemical property or really a chemical change. A chemical property is something that we can observe as a result really of a chemical reaction. Really, a chemical property is the ability of a substance to go through a chemical change or chemical reaction, or even the ability of a substance to resist sort of a chemical change or a chemical reaction. So a chemical change is different than a physical change. In a chemical change, what you start with and end with are two fundamentally different things. So what you start with in a chemical change and what it ends up with in a chemical change are two fundamentally different things. And the most important part of that is this: you cannot get back the original substance by any type of physical means. So you can't like throw it in the freezer to get back. You can't, heat it up to get it back. So by no physical means are you able to retrieve what you started with. So most chemical changes are referred to as chemical reactions. So for example, you took some hydrogen gas, not that. You take some hydrogen gas plus some oxygen gas, you will make some water. And that is a chemical change. Hydrogen gas, oxygen gas have very, very different properties than water, obviously. You could take that water, you could throw it in the freezer, you're not gonna get the hydrogen gas or oxygen gas back. You take that water, you could boil it, you will not get the hydrogen gas and oxygen gas back. Otherwise, none of us would make it to actually adding the pasta to the water, right? When you try to make pasta. So when you heat up water, again, it's just going to be sort of a physical change that's going to occur. It will not make it a chemical change. So this is a result of a chemical change. The only way you can actually get those things back is to actually do another chemical change or a chemical reaction. You can run an electrical current over water, and you can generate hydrogen gas and oxygen gas, which we will do in an experiment coming up. A little 9-volt battery, and you could break apart water into hydrogen gas and oxygen gas. So you would have to go through another chemical change. So that's the important difference. Physical change, what you start and end with, basically the exact same thing fundamentally. No real change in the substance has occurred. Maybe some physical aspect of it has occurred, a change. In a chemical change, that's all about that. What you start with and what you end with are fundamentally different things. Some type of change, chemical reaction has occurred. And again, you cannot get back your original substance through any type of physical means. Rust is basically a combination of iron and a little bit of oxygen gas, and it comes together and binds as iron 3 oxide, which is a new compound. And you can do whatever you want. You can put rust in the freezer, you can heat it up. You're not going to get the iron metal back or the oxygen back in that particular example. So that is a chemical change. Obviously, when we eat food and we go through digestion, it takes our food, breaks it down in all kinds of things, which are chemical sort of changes. Obviously, you can't get that stuff back. So a chemical change, the original chemical substance was the hydrogen and oxygen in this case. And they'd sort of vanish in terms of their original substances, but you can obviously make a new substance, which is water in this case. Obviously, a hard-boiled egg, kind of the same idea. As you heat it up, it alters sort of the yolk and all that good stuff, goes through a chemical change. And like I said, as we go and sort of enjoy it as well, we do get more chemical changes occurring. So a summary of physical and chemical changes. Once again, physical involves one or more physical properties, no changes to the fundamental substance. Again, the most common physical changes we see a lot in chemistry are the phase transitions going from solid to liquid to gas and back and forth between those guys. A chemical change, again, does involve some type of change to the fundamental component that was there. And again, the key part of that, like I said, you cannot really get it back through any type of physical means. As I said, chemical changes are what are referred to as chemical reactions. Silver tarnishes by reacting with substances in the air. Silver by itself has obviously that silver color. You react with something like sulfide, for example, you can make some tarnish there. Silver sulfide is now bonded together. And again, the only way to break those things apart would be some type of chemical change. Let's talk a little bit about some other things that we might have touched upon earlier, but just to make sure, an element is a substance that cannot be separated into simpler substances by chemical means. Elements obviously are on the periodic table there. Elements are thought of as like the alphabet, right? There's like 26 letters. But if you do some different combinations of the elements together, you will get different compounds along the way, just like we could get different words by using obviously our different letters and different arrangements. The basic unit of any element is the atom. And as we'll talk about in chapter 4, maybe, the atom is made up of our protons, our neutrons, and our electrons, right? So elements is as far back as you could go. The basic unit of any element are the atoms of those elements. Now, there are certain elements that are what are referred to as being diatomic, and that means that they are made up of two atoms. So like hydrogen gas, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. These guys here, they are all what are referred to as being diatomic. Molecules. Di meaning two, atomic meaning atoms, so they're made up of two atoms. So if you have hydrogen by itself, uncombined, it is two hydrogens that are bonded together. If you have oxygen by itself, uncombined, it is two oxygens that are bonded together. So these are diatomic molecules. Everybody else on the periodic table, when they are uncombined, are what are referred to as being monoatomic. Mono meaning one, atomic meaning atom. They come as one. By the way, good point to talk about, which is if you have any element that is uncombined on the periodic table, no charges. Yeah. So sometimes people think things always have charges. They don't have charges if they're uncombined. As we'll talk about when we talk about bonding, is when the metal and non-metal come together, that those guys actually do make charges. So nothing by itself, like if you had a piece of copper metal, it would just be copper, no charge or anything like that. And again, it doesn't get a charge until it combines with something. Now, these diatomic molecules are also elements. So these guys are elements as well. And they're also molecules. So each of these are elements and each of these are molecules. And the definition of a molecule is basically the combination of two or more atoms together. So that is the basic definition of a molecule. You need two or more atoms together. Those atoms could be of the same element like we have here. They could also be atoms of different elements like we have, say, with water, which is also a molecule. So we could have something like water, which is also a molecule. But water, as we'll talk about here, is not an element because it is made up of multiple elements there together, right? So elements has to be the same element involved, but they can be those guys of boxes. They can be molecules, those guys, the H2, the O2, the N2, and so forth. Any questions on that there? So speaking of molecules, just to make sure, a molecule is basically the combination of two or more atoms. And again, they can be the same like we saw there with our hydrogen. They could be different like we see with our water, or we see with our carbon dioxide. So all these are examples of molecules because frankly, they meet the basic definition of there's at least two atoms present. And again, they could be the same or they could be different. Only the H2 on top there is also an element. So the other two are not elements. The other two are actually compounds. And as we'll see on the next page, a compound is the combo of two or more atoms of different elements. So in order to have a compound, you got to have at least two or more different elements involved. And those two on the bottom there meet that criteria. Water has hydrogen and oxygen, so it is considered a compound. Carbon dioxide has carbon and oxygen, so it's considered a compound. They are both considered molecules because there's two or more atoms. But again, neither one of those could be considered elements because there's obviously different elements involved. H2 on top, again, is an element because it's only hydrogen. It is a molecule because there's two or more. It is not a compound, right? Because only hydrogen involved. So it cannot be a compound, the very top one. Any questions on the difference between those two words? Okay. So a compound, as I mentioned, you got to have those different elements involved. The difference, though, is you can break down compounds into elements by some type of chemical change. So as I mentioned before, if you ran electrical current over water, you could very easily break water into its elements. So if you ran an electrical current, you would get your hydrogen and oxygen. So once again, a compound to elements. But once you get to this point, you cannot go any further. So that again is as far back as you can kind of go. Now, the properties of compounds are usually very, very different than the individual elements that make them up. So for example, sodium metal plus some chlorine gas, makes a little sodium chloride, for example. Do a little balancing like it's a chemistry class. There we go. So sodium chloride, which is salt, right? So salt, which I think we'll use today, obviously has very, very different properties than sodium metal, which is a soft metal, and chlorine gas, which is a toxic green gas that you wouldn't want to be around. But through the magic of chemistry, when they come together in a compound, we can throw it on your fries and we're all good. Yeah, need it. So yay, chemistry. Yeah. Any questions on that? So obviously very, very different. Same thing with water, for example. Obviously hydrogen gas and oxygen gas have some very different explosive type of properties. For example, water, when they come together, obviously very, very stable than say hydrogen gas or oxygen gas in that case. Any questions on that there? So the next thing we're going to talk about is mixtures and pure substances. A substance is any form of matter that has a definite and constant composition. So a pure substance is pretty much anything you got by itself, right? So this idea of pure substance. So if you have just water, just H2O, that is considered a pure substance. If you have just ammonia, which is NH3, that would be considered a pure substance. If you have just gold metal, it would be a pure substance. Substances differ from one another in their composition and can clearly be identified by smell and taste. Don't eat or smell anything in the lab, but if you ever smell like Windex, necessarily have ammonia in it, but an ammonia type cleaner like that definitely has a very different odor than, say, water's odor, hopefully. So you could usually identify them by odor and stuff like that. Sometimes visually, though, color and stuff like that, you can't, right? So a lot of solutions and stuff like that, or liquids, are really kind of the same color or colorless, so you might not be able to identify that. So what happens when we take two or more substances and put them together? We get a mixture. So a mixture is a combination of two or more substances together, and that makes a mixture. So for example, if I had water by itself, that would be a substance. Bless you. If I had sodium chloride solid by itself, that would be a substance. If I took the water and I took the sodium chloride and put them together, the sodium chloride would dissolve in the water like we're going to do in lab, I think, today. And I will get a mixture of the two, which basically would be salt water, which is sodium chloride, which is the aqueous. Aqueous means basically dissolved in water. And I would get a sodium chloride solution or a salt solution, which is a mixture of the two. A really important part of mixtures is this: although you mix them together, and although they may look like something has gone away, something has just vanished, they don't. So the individual substances in a mixture will retain their identity even after you mix them together. So when we take salt and water and we put it together, frankly, it just looks like water's in there at that point when the salt dissolves. Right? If you take some salt water out of the ocean and get just the water, nothing else floating in the ocean, you look at it and just look like water, right? But if you taste it, it's kind of salty, right? So it's got obviously stuff dissolved in there, but we can't see it sometimes. But it is still there, and it is still there in its original form, and you could actually get it back by some type of physical means. So by some type of physical process, you're able to achieve back your original substances. So there's really two types of mixtures. One is a homogeneous mixture. A homogeneous mixture means that after you mix together the substances with sufficient mixing, everything will look the same throughout. So everything mixes really well. So my sodium chloride example there, if we take the salt and we take the water, the salt will mix, right, and dissolve into the water. Visually, when we look at it, it looks like the salt's gone, just looks like water that's in there, but it will mix perfectly together. Is the salt really gone? The answer is it is not. It's just hiding in the water and you can't visually see it. So although it looks like it just went away, maybe it reacted, you might think it did, but it actually didn't. It just got kind of mixed up in all the water that's there, and visually you can no longer kind of see it. The other thing, or another example, would be sugar, right? You take a little sugar and put it in your water, you can mix it, it will dissolve, and that would be a homogeneous mixture. The other type of mixture is a heterogeneous mixture. And unlike a homogeneous mixture and a heterogeneous mixture, you can mix that thing all day. You will still see the different sort of layers or phases that are there. So if you take some sand and water, for example, like we'll do today, you can mix that sand all day, right? The sand's never going to dissolve in that water. You look at it, you will always see the sand in there, right? And it's definitely a heterogeneous mixture. So heterogeneous, you see different layers, things really don't mix and look the same. Homogeneous, when you mix them, everything looks the same and looks the same throughout, and they mix really well. Nicer example of a heterogeneous would be chocolate chip cookies, right? You can still see the chocolate chips in the cookies, right? So that's a good example. We should really do that lab instead of what we're doing today. But a heterogeneous mixture, again, you can see those different sort of phases. Now, regardless of the type of mixture that you got going on there, whether it's a homogeneous mixture or whether it's a heterogeneous mixture, you could do some type of physical process to really get back all of the original substances in their original forms. So for example, got somewhere I could scribble maybe. Yeah. So for example, if we took the, say, beaker of, we'll kind of do like our example today in class here. We got some sand in there. We have some salt water. When we look at this mixture of, say, salt water, with sand. The mixture of the salt water and the sand is what type of mixture? It is a heterogeneous, right? You can see the sand in the salt water, right? The salt water by itself is what type of mixture? Homogeneous mixture, right? The salt water just by itself, without the sand there, is a homogeneous mixture. When you look at it, it looks like water. So let's say we wanted to separate this out. We'll just call this our pre-lab lecture right now. Here we go. So you can take something like a physical process known as filtration, right? You take a funnel, you put some filter paper up there. You wonder why your funnel got really short there. Maybe you put it into a beaker to catch it would be a great idea as well. And I'm going to pour this mixture in, right? When I pour this mixture in, what is going to be trapped on the filter paper? Yeah, so all the sand, right, will be trapped on the filter paper. All of our liquid will go through, right? And in this case, that liquid would be our salt water, right? So by this very simple process of filtration, a physical process, we're able to actually separate one part of our mixture. We could get the sand. If I took that sand, open up my filter paper, let it dry out, put it in the oven, I have nice dry sand like I started with, right? So I was able to get back that. Now, if I take my salt water, and this is not what we're going to do, but we're going to do sort of a version of this. But if I take my salt water and I put it into this apparatus, really terribly drawn here, but they're basically two sort of flasks just connected by a tube, and this tube is really cold. And I take my salt water and put it on one side, and I decide I'm going to heat this side, right? This is sort of a closed system. As I start heating the left-hand side here, what's going to happen to my salt water? Yeah, this is a homogeneous mixture, right? As we start heating it, the water part of it is going to start to evaporate, right? You're going to heat it up. It's going to start to evaporate. And as it starts to evaporate, that means I'm going to create steam, which basically is still water. That steam has nowhere to go but go through this very, very cold tube. What happens when we have steam, which is the gas version of water, and you cool it down? It goes through condensation, right? And it's going to create liquid water, which will drop out on to this side. If I continue this process, I will end up with water over there. And on the left-hand side, what will happen is eventually my whole entire thing disappears. It's okay, we can redraw, we can rebuild. Looks just like the original, maybe it changed a little. And as we continue to heat, all the water will evaporate, and what we will be left with on the left-hand side would be all of our salt, right? So even this homogeneous mixture where we couldn't even visually see the salt at all, right? We were able to separate it out. I'm not sure why it's blue, but we'll go with blue since it's this color. But we could take the salt again and just really dry it out, and we obviously would have our salt just like normal. We could take obviously our liquid water here and collect it, and that would give us both of our substances that was in salt water. And through these two physical processes here, we were able to separate out all three of the substances back to their original form, right? All these processes, right? And when we make mixtures, is it a chemical change or a physical change? When you make a mixture, it is a physical change, right? And we proved that by doing this process. We got our salt back, we got our water back, and we got our sand back. None of those changed anything new. And if they did, that would be a chemical change. But because they did not, and we could get it back by physical means, that is a physical change when you make a solution, when you make a mixture. This, by the way, is what is referred to as distillation. Hang on one sec, we'll finish up. Much prettier picture of it, which is right here. There we go. So here's a prettier picture of distillation. Looks sort of like mine if you close your eyes, but the same idea here. That's our homogeneous mixture of just salt water in this case. Heating it up allows it to evaporate. We collect the water. We have the salt left over. Again, a physical change. We're essentially going to do this in lab, except we're going to do it with an evaporating dish. So as you heat it, all the water just escapes. We're not going to collect it, but what should be left in your evaporating dish at the end will be your salt. Yeah. Any questions on this? Congratulations. We will lay it up there. That is chapter 3.